on this stage, we have Shahar Papini.
Hi there.
And from Starkware, and yeah, welcome to the stage.
Thank you very much. Hey, yeah, so the title of my talk is not Deep Stark Tricks, like I said. I lied, sorry. It's about lookup with Starks, or the recent small work me and Ulrich from Polygon did. So here it is. All right. So I'm going to explain a bit of preliminaries about Starks and lookups and products and GKR and Sumchecks, like to give you background. So I hope most of you will understand what's going on. And I want to say that most of the things I'm going to show here are not anything we did, or like known things, the things smarter people did, but I'll present them anyway, so you'll see. Okay, so in very high level, what's a polynomial commitment scheme? There are two sides in this proof system, the prover and the verifier. The prover gives some kind of oracle access to a polynomial of his choosing. He chooses a polynomial and kind of gives it to a verifier, and the verifier can sample this polynomial at some point and know it's the right value. All right, so in our context, we are talking about two polynomials, as you can see from the right, P of x and Q of x. And we're interested only in some subset of the points, some domain D, and not all of the points, like you see here. I don't have a laser pointer, but yeah. Okay, so Starks are a tool that lets us prove some kind of local relations on polynomials. Something, for example, some relation on the current row, or one row and the row after, or something local. But we want to prove some kind of global relation. And for that, we are going to use a lookup. Okay, so I'll start with a simple one, a permutation argument. Well, imagine I have these two polynomials and their values on the domain. And I want to show that all the values of P on this domain are exactly the same as the values of Q on this domain as a multiset, or one is a permutation of the other. As you can see in this example, P is 5, 4, 3, 2, 1, and Q is 1, 2, 5, 3, 4. These are permutations. It's the same multiset. So this should work out. And the way we do this is by checking basically the product of all the values, but we don't want the prover to be able to cheat, so we first shift this point. We compute the product of Z minus the value. Okay, so we want to show this product is the same for P and for Q. To do this, we'll add another column. We call it the cumulative product polynomial. And this polynomial would be the product of the values of P until this row and the values of Q until this row, the shifted values. And to verify that this polynomial is true, it's just involving local relationships, so we can do it with Stark. For example, one cell of the cumulative sum is equal to the cell above it times Q over P, something like that. So it's a local relation that at each step we multiply and divide by another thing. Okay, so after we do this, we basically need to verify that the last cell is 1, because it's the product of the one column over the product of the other column. It should be 1 if they are the same. And the cost of this proof is the cost of using two polynomial commitment schemes for P and Q for our input values, and one for the cumulative cumulative product column, which is an extension field polynomial, because if we're talking in the realm of small fields, P and Q can have a small field value, but the Z shift we have for the column needs to be from a large field. So this column over the right might be a big field column, an extension field column. So this might be kind of expensive, and we would very much like to avoid it if possible. But this is the regular permutation argument. Okay, so now lookup. Okay, lookup is another lookup argument. It doesn't want to show that the values of P and Q are the same as multisets. It wants to show that the values of P are contained in the values of Q. There's a type over there. Over the right, it's supposed to be Q. So here's an example. If you can see P, its values are 1, 2, 1, 1, 4, 2. And they're a subset of the values of the table over the right, 1, 2, 3, 4. If I said Q, it's supposed to be T. There's polynomial P and T for table. All right. So I want to show that all of the values on P appear in the values of T. So we're going to do something kind of similar. Instead of computing the product of all of the values, we're going to compute the sum of 1 over the value, shifted. It's pretty clear that if we have two columns that are permutations, the sum of 1 over the values is the same as the sum of 1 over the values on the right side, because we can just swap the order because it's symmetric. So basically, we take all the values on the left, like 1, 2, 1, 1, 4, 2, and we group them. Group them into 3 instances of 1, 2 instances of 2, 0 instances of the value of 3, and 1 instance of the value of 4. And on the table side, instead of duplicating all the values and writing 1 3 times, we only allocate 1 row for the value 1, and add another column for the multiplicity, for how many times it appears on the left. So if we compute the sum of 1 over the values of P, and show it the same as the sum of M over the value T on the right, meaning 3 times 1 over 1, and 2 times 1 over 2, etc., then it should show that these are the same values as permutation, or that every value on the left actually appears in the table on the right. And we shift the values so the prover can't cheat. All right, what is the cost of this thing? Like previously, we have this one commitment on P. We have an extension field commitment of 1 over the values, because we need to compute 1 over the values to be able to sum them. And we have the same thing on the right side. We have 2 columns, T and M, and 1 extension field R, but usually these columns on the right, they are smaller. So I call it a small number of M-sized polynomial commitments. So note here that we also have this extension field column, which also is kind of expensive, and we would like to avoid it if possible. Okay, so this is a lookup argument. All right. So yeah, like I said, both primitives require extra commitments to the cumulative product and the 1 over the value for the lookup, and there are extension field commitments, and we don't want that. And an observation from the Lasso paper, if you were the Lasso lecture earlier, is to use GKR for this. Okay, so nice letters, GKR, but what do they mean? I'll try to explain what GKR means, and hopefully I can, you won't get lost too much. All right, so Sumcheck and GKR. So I'll start by describing Sumcheck. Maybe some of you know Sumcheck. It's a protocol that proves the sum of the values of P over D. It works on multivariate polynomials, though, not univariate. Multivariate means polynomial with a few variables, and the sum is always the sum over the hypercube. Hypercube basically means that for every x, you put either 0 or 1. So you have 2 to the n values, 0, 0, 1, 0, 1, 1, 1, 1, 0, 0, etc. Okay, so this Sumcheck protocol lets us prove that the sum of the values of p over the hypercube is something. Okay, how this protocol works, it's pretty simple, but yeah, simple. Okay, so first of all, p sends the value he claims is the sum. This is a0. Now he wants to show that this is indeed the sum, so he computes another sum where instead of summing over the first coordinate b0, he replaces it with a variable x. So he computes this sum below, f0 there. It's a sum only on the coordinates that are not the first coordinates. And the first coordinates we put this variable x. Now this is a polynomial in x, a polynomial of low degree, like let's say h is of degree 5 in every variable. So f is just a polynomial of a single variable of degree 5. So p can just, the prover can just send all the coefficients of this polynomial. And it's really succinct. Okay, now that the prover sent this f0, V needs to do two things. The verifier needs to do two things to make sure that everything is correct. One, he can use it to and put, instead of x, he can substitute 0 and 1 and compute that he indeed gets a0 for the sum. Because supposedly h, if you put f0 at 0 and f0 at 1 and you sum, you get all the sum of the hypercube. So f0 needs to be consistent with a0. The other thing you need to see is that f0 is indeed, as the prover claims, that it's indeed this sum over h. So what he can do is substitute a random point instead of our x. Random point r in, let's say it's in a big domain, a very big domain, an extension field. And it is known that if we have two univariate polynomials and they are equal at this big random point from big space, then they're probably the same polynomial. So if we can show this formula for the formula, when we put r instead of x, then it's probably the correct polynomial f0. Okay, but this new problem we need to show to the verifier is again a sum check with one less dimensions. So we repeat this rounds log n times, and we get log n rounds, and at the end the verifier says, okay, so now we need to I get that h on an r0, r1, r2, r3. I got that the prover needs to show me this point when I take h and substitute some random point that got from all the rounds. And this is where we need some polynomial commitment scheme for the polynomial p. H. P is the same as h. Okay, I need some polynomial commitment scheme for the polynomial h, where I need to, the prover needs to show to the verifier that h on these random values are what expected from the Sumcheck protocol. So I repeat, it's log n rounds. Each time one coordinate gets set to random number, and at the end, I need the prover needs to prove that h of one r0, r1, r2, r3, etc. is something. And this is just a polynomial commitment scheme. All right. Let's see. Okay, so now that you have Sumcheck, what about GKR? How does GKR work? Well, GKR is a protocol based on Sumchecks that can prove that an arithmetic circuit evaluates to something. Imagine that you have one of these columns, let's say it's P, polynomial. I envision it right now as a row, but it was a column before. And I look at all of its values, and I build this arithmetic circuit on top of it. I I create this layer of outputs, and each output is some gate. Let's say addition of two values in the input layer, or multiplication of two values in the input layer. And I repeat this and get an arithmetic circuit that is built with multiple layers. And at the end, I have this one value. And I want to show the prover that the value, when I put in as inputs my polynomial p, I want to show that the value at the end is something, let's say 15. So how can I do this? I'm going to do this with Sumcheck. Now, it's important to note that while P is given as a polynomial commitment scheme, none of the other layers are ever committed on. They are just they're not committed on. The prover just needs to compute them, but not hash them, not do polynomial commitment scheme, nothing. And this is where we are supposed to gain. All right, so let's start with an observation about multilinear polynomials, which will help us for the GKR. Okay, given some f is a multilinear polynomial, which means it's a polynomial of a lot of variables, x0, x1, x2, x3, x4, but the degree in each variable is at most 1. Okay, and now look at this specific polynomial I just showed. It's called ek for equal, ek x xb. This polynomial, okay, it's a complicated expression, but let's look at specific example for 0, 1, 0. If I put instead of b 0, 1, 0, how does polynomial look like? It looks like 1 minus x0 times x1 times 1 minus x2. What this actually means, it means that if x0 is 1, then this polynomial will be 0, because the first term will zero out. If x1 is 0, again, this zeroes out. And if x2 is 1, then this zeroes out. So basically, the only time when I put instead of x binary values, and it's not 0, is only if x0, it's not 1, it must be 0. x1 must be 1, x2 must be 0. So this polynomial is actually the polynomial that gives 1 on b, and 0 everywhere else on the hypercube. Which means it's the Lagrange polynomial. Basically, we can use this to interpolate every polynomial and represent it as the sum as Lagrange polynomial. So basically, the thing we see below. Any f of x is the sum of the hypercube of the value at point b times the Lagrange polynomial at b. This is a polynomial that is 1 on b and 0 everywhere else. So in multilinear polynomials, the Lagrange polynomial is very nice. It's very succinct. And we can use this to do nice things like GKR. All right. Okay, so how GKR works. Like I said, we have an arithmetic circuit and it has layers where the input layer are called W0, the next layer is W1, the next layer is W2, etc. And each one is a multilinear polynomial. And it represents the entire values of the layer. And the idea of GKR is to reduce a query to a low layer into a query to a layer above it. So imagine I have this circuit that ends with a single value, and I do a query to this single value, which is just the value itself, and reduce it to the query to the layer before, until I get the query to the input layer. And then I use my polynomial commitment scheme to compute this query at the input layer. All right, so how does this reduction work? Let's say I have this random query to layer L1, L plus 1. So I need to compute the polynomial WL plus 1 at R. Remember, WL plus 1 is a multilinear polynomial that has all the values of this layer in the arithmetic circuit. So what can I do? First, I'll represent it using our trick. As you can see here, WL plus 1 at R is the sum of the Lagrange polynomials at R, or the sum of all the positions O on the hypercube of the value of this layer at O times the Lagrange polynomial at given it the query R. Okay, now we need to see that WL plus 1 at O, it's just a value. It's not, we don't really need to think about it as a polynomial or anything. It's simply the value of this layer at O, and this value has a representation as gates of the input layer. Because, okay, it's an arithmetic circuit, and it means that every value in this layer is an output of some gate, which means either some addition of two inputs or a multiplication of two inputs in the input layer, in the previous layer. So I can just open this expression, WL plus 1 at O. Generally, okay, this is a general formula. I'll get some more specific formulas later, but generally, we say that WL plus 1 at O is actually just a sum on two input indices times, this is a selector that is 1 if there is a multiplication gate here and 0 otherwise. So if there is a multiplication gate here from I0 and I1 to O, then it's just a multiplication of the values on the previous layer. And there's a sum here because there is the same thing for addition gates. So imagine there is the same sum, but with a selector for addition gates and the sum of the two input values. All right. Okay, now that I have this expression, I know that proving the value to the right is just a sum check. I have this sum of some kind of polynomial after the summation. And this polynomial is basically a description of the arithmetic circuit. And this is the previous layer, and this is Lagrange polynomial. And for the sum check, we want to be able to query each polynomial at a random point. And we can do this for more because the verifier should be able to know that. This is simple. And when in the sum check we actually need to sample WL, the previous layer, we get stuck. But actually, this is the reduction. To compute the sum check, we need to compute the query to the previous layer. So we started with trying to compute a query to layer L plus 1, and we got that we need to compute the query for L. So we repeat this reduction until we reduce query to the last layer, which has no variables, to the first layer. And then we use our polynomial commitment scheme. All right. Okay, so this is an application of the GKR for the grand product. And I remind you, grand product is just being able to compute the multiplication of the entire column. So the arithmetic circuit we're going to choose here is a simple binary tree. Every two aligned values are going into a multiplication gate and have one output. So basically this binary tree computes the multiplication of everything in this column. And for every reduction from a layer to the previous layer, I need to do a sum check. The size of the sum check here is 1, previous 2, 3, 4, 5, until I get to the very first layer, which is log n. So the total number of rounds is 1 plus 2 plus blah, blah, plus log n, which is log squared n. So this is the number of rounds we have for the GKR. The degrees are degree 2. And in this case, we have an even simpler formula for the sum check at each layer. We can see that the layer it's L plus 1 is the sum over all indices B here over the hypercube. And each value is just a multiplication of two values above. at the value at B is a multiplication of the input, the previous layer at B0 times B1. So it's like a really simple formula that we can use for the GKR for the grand product. All right. So what's nice here is that we actually save. We don't need the cumulative product column at all, like we had at the beginning. This saves the need for an extension field polynomial commitment, saves a lot of commitment pressure. We do have extra rounds, need to pay attention for that. And this requires a multilinear polynomial commitment scheme, because like we said before, at the end we reduce everything to query to P of X at a multilinear point. So yeah, this is a caveat, but we'll address it later. The last point. Okay. Now we would like to do the same thing for the other lookup argument, the logup. Okay, so here we start the thing that me and Ulrich did. Other stuff, we didn't do anything. This is just an observation we had. A pretty simple one, I might add. Basically, we want to do the same thing for the logup. Now, a logup is not a product of a column. Instead, it's a sum of reciprocals of the columns of 1 over the value. And GKR can't really do divisions because at each step, we need to get this polynomial. And multiplication is a polynomial, addition is polynomial, but division is not. So the observation here is to use projective coordinates, which just means look at the representation of the number as a fraction and keep this and never do the division itself. So like in school, if we had A over B plus C over D, it equals AD plus BC over BD. So we just compute the numerator and denominator and don't do the division ever or until the end. And now we have this kind of circuit, that the input to the circuit has the numerators and denominators of the input, and the binary tree takes 2 pairs and outputs 1 pair of numerator denominator. And now this is a GKR problem, because we don't have divisions, everything is multiplication and addition. Right, these are the formulas. Basically, you can see here, imagine that we have a lot of pairs numerator denominator for the input layer. So the next layer has half as many values. The denominator is just the multiplication of the previous denominators, as you can see above. The numerator is kind of a product of the numerator and the other denominator, and the other numerator and this denominator. So yeah, we have a bit more multiplication than we had at the previous example, at the grand product, and also have more values, twice as many values, but we can still do it. Yeah, here I present this as if it was 2 different polynomials, N and D, for like different layers. You can do it like that. You can also batch them together, or maybe we present the layer as interleaved values. All of these are applicable, and these are the formulas we get for the sum checks. All right. Okay, we get here 2n degree 2 gates instead of just n, because I have numerator and denominator. It's a bit more expensive, twice the gates, 3 times the multiplications. And again, this requires a multilinear polynomial commitment scheme. Okay. So this was the logup GKR. I don't have a lot of time. Maybe I'll skim through it, but this is a way to compute the multilinear polynomial commitment scheme in a univariate case. Yeah, GKR is great, requires multilinear polynomial commitment. There are known constructions to prove a multilinear commitment over univariate, and this is just another one. It plays well if you're doing a lot of lookups and univariate stocks. So, how does this look like? Okay, the idea is that I can look at a column, it's a column in two ways. Imagine this is a polynomial. These are also the evaluations of it as a univariate polynomial, but I can also think about it as evaluations of another multilinear polynomial on the hypercube. There is this duality, and I can try to evaluate the value of this multilinear polynomial with the trick we saw before. This is the trick up here, that every multilinear polynomial at R can be computed as the sum of its interpolants using the Lagrange polynomials. It's the sum of its values times the Eck polynomial. And we can do this sum over the univariate Starks with just cumulative sum or just a sum. But the thing we're missing here is the interpolant column. In the multilinear case, it was easy. It was a succinct expression, but when we actually do it in a univariate Stark, this expression 2 bits of I is hard because the X is a univariate point. It's not multilinear point. So how we do it by introducing a new column, which is the Lagrange polynomial, evaluated at the random query R. And we can see that it has a nice structure, and we can use a very low number of constraints to just make sure it's correct. For example, if we look at an even and odd row, the ratio is just R0 to R1 minus R0. And we can say things about row 0 and 2 for the next bit. So we can create these log n constraints to make sure that this column is correct with the Lagrange polynomials. And then we can do a cumulative sum or a column or just the multiplication of the Lagrange in the polynomials. So we can batch a lot of columns that we want to sample each one at a point and do all of these with just 2 extra columns. It's true that these are 2 extension field columns, but we do them for all the lookups, and all the stocks just need 2. So let's say we have, 20 lookups. Instead of adding extension field for every lookup, we just add 2 columns. All right. I'm out of time, I guess. So no questions?